Assalamualaikum warahmatullahi wabarakatuh and greetings. My name is Fazilah binti Kamal and my metric number is 63215. I am under supervision of IR Dr. Muhammad Daniel bin Ibrahim. My title for my final year project is Plunger Thermal Visualization for Die Casting Improvement using Volume of Fluid or VOF. First of all, die casting is a process of molten metal that is injected into a mold cavity at very high speed and pressure to produce complex and precise products. Based on Figure 1, there are two types of die casting processes, which includes horizontal cold chamber system and vertical injection system. The advantages of die casting process includes the high production rate, exceptional dimension repeatability, and less machining due to the less casting finish stock. Butler et al. Says that die casting consists of three main phases. The plunger movement is separated into three different phases. The first one, the slow shot phase. The second one, the die filling phase. And the third one, the pressurization phase. With the technology of die casting that may produce an excellent cast parts, there are always risks of any defects formed due to high injection rate. The occurrence of defects is usually due to porosity. The frequent casting defect causes by the imbalanced fluidity behavior of molten metal, as well as the inconsistent thermal distribution in the plunger. Hence, gas bubble is not fully released and entrapped during the injection procedure and cause porosity to the products. Injection speed in the plunger is one of the main features affecting the development of porosity. The injection speed must be optimized, or else the turbulence liquid flow causes limitation to the air from escaping the mold and hence entrapment of gases occur. Meanwhile, as the velocity of the molten metal in the plunger is too time consuming, it may cause backflow instead. Furthermore, high imbalanced thermal distribution also cause porosity to the cast parts. Defects will affect the mechanical properties of the cast parts, such as the tensile strength, yield strength, and lifespan of the cast parts. The quality of and appearance also may happen if the parameters during the die casting progression is not adjusted. Objective of this project, which is to complete CFD simulation with alteration of variables. CFD analysis is one of the best analysis. The second one is to identify the effect of temperature and velocity distribution of molten metal in the plunger. And lastly, to compare the simulation results between the optimized parameter. By using the computer-aided flow simulation technique, it enables the engineers and designers to construct a new method to analyze casting defects at early stage of mass production. Based on the first theory, which is from Murray, it is important to have certain set of variables, which is temperature and pressure, to complete the die casting procedure. While in the second theory, Ibrahim says that computer flow simulation is really important and helpful to optimize the procedure as well, going through the defect analysis before any die casting processes. While theory 3 stated that magnesium has a lower latent heat for solidification and leads to shorter casting cycle times compared to aluminium. Ibrahim et al. On 2020, they illustrate the X-ray CT scan gas porosity marking for the conventional test piece product. From the figure, the purple dots in the figure indicate the occurrence of air entrapment in the die cast product. X-ray CT scan result close-up illustrate that most of the air entrapment is focused on the test piece part with a thickness of 16 mm. The figure shows the before filtered and after filtered X-ray CT scan result. From the study, it was found that the defect volume thickness of 16 mm was 47.73 mm3, where it is covered 80% of the total defect present in the cavity. Thus, in this study, the parametric modification is done to analyze the outcome focusing at the thickest part of the test piece. The design of the mold system includes the short sleeve, plunger, biscuit, gate, cavity, and overflows. Each system serves a distinct purpose by directing molten metal from the injection molding to the cavity. The phase started with the injection of molten metal from the short sleeve, passing through the biscuit, flowing through the runner and gate, and quickly approaching the casting stage. This research focuses on the performance of the molten metal throughout injection. Framework of the study will be based on the simulation. Next, the figure shows the thermodynamic parameter as well as the solid parameter. As we can see from the solid parameter, in every injection molding operation, it is recommended to preheat the die surface and maintain a minor temperature difference between the molten fluid and the mold. The recommended preheat temperature is between 420 to 660 Kelvin. The molten metal injection speed for this project was 1, 2, and 3 meter per second and follows the parameter of the MP450 machine. Meshing is a crucial element of the engineering simulation process, in which complex geometry are broken down into individual parts that can be employed as discrete local simplification of the wider domain. The mesh quality has a major effect on the CFD result. The longer the solver works, the more cells there are, and fewer cells can result in inaccurate results and findings. The meshing tetrahedron form was constructed using a 0.5 meter element size in this research. Any 3D volume, despite of shape of topology, can benefit from the tetrahedral meshing shape. The basic guideline of tetrahedral grid skewness for most flows should be kept under 0.95 with an average value of below 0.33 according to the ANSYS Fluent documentation. The maximum skewness is 0.89224, whereas the average value is 0.26853. Furthermore, the cross-sectional mesh of the casting system in this work, such as runner, gate cavity, and overflow, from a complicated mesh. Because of this complex geometry, the number of knots on those components increased compared to the short sleeve and biscuit. The graph has skewness to the right and maximum element metric in the range of 0.12 and 0.23. System reliability meshing. The high-quality mesh developed is essential for generating stable legal unit and dependable CFD solution. Magnesium alloy replenishment for injection is passed out within rod shape to maintain safety and improve the precision of the injection process. Due to absence of an external furnace, most air is diverted away from the machine, thereby lowering oxides generation. Additionally, when oxides are reduced from the device, less maintenance is needed. Based on the table, these are the comparison of conventional type and V-line system. Conventional type cold chamber is a high pressure capacity is needed because the nearly hardened biscuit is pressurized at a very high pressure, likely to result in pressure loss on the inside of the wheel. And the V-line system is applying pressure directly to the molten material. The material is transferred to the finer portions of the device. This research looked at the fluidity of molten metal coming out from the short sleeve. This will be to assure that the molten metal injected into the mold cavity completely fills the cavity and prevents incomplete filling. Due to the acute corner of the test specimen is the key portion for evaluating 90-degree angle products, the molten metal must completely fill the mold cavity to ensure that the product meets the regulation. Flow simulation parameters such as inlet velocity, original molten metal temperature, and pressure are being used to observe the molten metal fluid flow. The figure shows the CAD drawing of the die casting system consists of the short sleeve, biscuit, runner gating system, and the cavity. The drawing as well the dimension of the cavity is received from Kyokuto Die Casting, Japan. The molten metal input velocity is very crucial in determining the molten metal velocity streamline pattern inside of the cavity. On the standard mold design, the parametric machine value for entrance velocity of molten metal specified by Kyokuto Die Casting, Japan, is 2 meter per second. 2 meter per second is a reasonable speed that prohibits molten metal from backflowing into the mold cavity, decreasing entrapment and increased industrial efficiency. The total length of the plunger is 250 mm. Therefore, the short sleeve is divided into 3 parts, which are called plane 1, plane 2, and plane 3. The average of pressure at critical point will be calculated once the molten metal reach plane 1, 2, and lastly plane 3. As pointed out, a high pressure is desired at critical point to aid the air pocket to disperse and help reduce gas porosity. Moreover, another plane named plane 4 at YZ axis is generated to help of visualizing temperature contour and velocity streamline. The figure below portray all the planes mentioned. The figure shows the molten metal magnesium when it reaches plane 1, plane 2, and plane 3. As it hits all the planes, the pressure at the critical point will be taken. As mentioned, highest possible pressure at the critical point is desired to disperse the air entrapment and avoid porosity. Based on the graph, the 3 highest pressure at the critical point is chosen from 9 configurations. The 3 configurations are 30 MPa with 1 meter per second of velocity, 50 MPa with 1 meter per second velocity, and 50 MPa with 3 meter per second velocity. Next, with the 3 configurations mentioned earlier, we are going to see the 3 main points called point 1, point 2, and point 3. These points are located as shown in the figure, as it is a crucial pathway of the short sleeve plunger system. Too high temperature, pressure, and velocity can cause wear and tear to the system. For these vital and crucial points, it is best to choose the lowest of temperature, pressure, and velocity in order to increase and sustain the lifespan of the machine. Hence, we can reduce the cost of maintenance and high productivity and efficiency as less maintenance are required. The graph represents the velocity, pressure, and temperature for the 3 configurations that has been selected. The values for all parameters are the average values taken throughout the casting process. As we can see, the last configuration, which is 50 MPa 3 meter per second, have the highest value for velocity, pressure, and temperature. This portrays that this particular configuration is unsuitable to be used for this project. As stated earlier, high velocity, pressure, and temperature can cause the plunger to reduce its lifespan. Next, the first and second configuration has similarity in the values of velocity and pressure. Yet, the first configuration shows slightly lower temperature, whereas the velocity of the first is higher. Temperature can give more effect to wear and tear compared to velocity. Hence, the first configuration of 30 MPa with velocity of 1 meter per second is chosen. A lot of variables have been simulated to find the best configuration for the die casting process. To conclude with the proposed configuration, we can attain the high pressure at the critical point as desired to disperse the air bubble, yet we can maintain low pressure, velocity, and temperature at the plunger, which helps to increase the lifespan of the machine. In this project, simulation software ANSYS was used to analyze the injection process and helps in predicting the critical location for casting defects to occur on casting parts. ANSYS software code is fluid flow analysis by changing the design virtually and undergo simulation as the same as actual injecting molding process. Critical point was determined from the past research, hence modification to the parameters is needed to help in finding the best configurations. As recommendations, experimental approach is suggested to verify and compare the data obtained from the simulation approach. A more reliable software such as JSCAS, Mode Frontier, and Microsoft needs to be utilized to get a better result. The software that is mentioned can automate the workflow, run the process, monitor execution, and automatically analyze results for different conditions.